Electromagnetic waves are fundamental to our understanding of physics and technology. They are responsible for everything from radio transmissions to visible light and even X-rays. In this video, we'll explore how electromagnetic waves are generated, their properties, and their wide-ranging applications. We'll begin by examining the historical context, including Maxwell's revolutionary insights, and then move through the mathematical foundations, practical examples, and the electromagnetic spectrum. By the end, you'll see how these waves shape our daily lives and scientific advancements. James Clerk Maxwell, a pioneering physicist, realized that a changing magnetic field creates an electric field, and vice versa. This mutual relationship forms the basis of electromagnetic waves. Maxwell's equations unified electricity and magnetism, showing that not only electric currents but also time-varying electric fields generate magnetic fields. This insight resolved inconsistencies in Ampere's circuital law and led to the concept of displacement current, which is crucial for understanding electromagnetic wave propagation. Ampere's circuital law originally described how electric currents produce magnetic fields. However, Maxwell noticed a contradiction when applying the law to a charging capacitor. Depending on the surface chosen, the calculated magnetic field could be zero or non-zero. Maxwell resolved this by introducing the displacement current, which accounts for the changing electric field between capacitor plates. This addition ensures consistency and completeness in electromagnetic theory. Let's visualize the process of charging a capacitor. When a current flows through a wire, it creates a magnetic field around it. Using Ampere's law, we can calculate the magnetic field at a point outside the wire. However, if we choose a surface that passes between the capacitor plates, no current crosses it and the magnetic field appears to be zero. This contradiction highlights the need for displacement current, which arises from the changing electric field between the plates. Between the plates of a charging capacitor, the electric field changes as charge accumulates. This changing field generates a displacement current, which acts like a real current in producing a magnetic field. Maxwell's equations show that both conduction current and displacement current contribute to the total magnetic field. This concept is essential for understanding electromagnetic wave generation and propagation. Maxwell modified Ampere's law to include both conduction and displacement currents. The new law, known as Ampere-Maxwell law, states that the magnetic field is generated by the sum of conduction current and displacement current. This law is a cornerstone of electromagnetic theory and explains how electromagnetic waves can propagate even in the absence of physical charges. Maxwell's equations are four fundamental laws that describe how electric and magnetic fields interact. They include Gauss' law for electrostatics, Gauss' law for magnetism, Maxwell-Faraday's law, and the Ampere-Maxwell law. Together, these equations explain the behavior of electromagnetic waves and unify the concepts of electricity and magnetism into a single framework. Electromagnetic waves are transverse waves, meaning their electric and magnetic fields oscillate perpendicular to each other and to the direction of propagation. These fields vary sinusoidally and are always in phase. Unlike mechanical waves, electromagnetic waves do not require a medium to travel. They can propagate through a vacuum, carrying energy and momentum. Electromagnetic waves possess several unique properties. They are non-mechanical, meaning they don't need a medium to transfer energy. The electric and magnetic fields oscillate in phase and their direction of propagation is determined by the right-hand rule. The speed of electromagnetic waves in a vacuum is approximately 3 × 10⁸ ms, and their energy is distributed equally between electric and magnetic fields. Electric and magnetic fields in an electromagnetic wave can be described mathematically as sinusoidal functions. For a wave propagating in the positive x direction, the electric field E and magnetic field B are given by E equals E0 sin kx omega and B equals B0 sin kx omega. Here E0 and B0 are the amplitudes, k is the wave number, and omega is the angular frequency. The speed of the wave is determined by the ratio omega/k. In electromagnetic waves, the magnitudes of the electric and magnetic fields are related by E equals Cb, where c is the speed of light in vacuum. This relationship ensures that the fields are always proportional and in phase. In different media, the speed of electromagnetic waves changes depending on the medium's permittivity and permeability, affecting the refractive index. Electromagnetic spectrum encompasses all types of electromagnetic radiation, from radio waves to gamma rays. It covers a vast range of frequencies, wavelengths, and photon energies. Each region of the spectrum has unique properties and applications, such as radio communication, medical imaging, and visible light detection. The spectrum is classified by increasing frequency and decreasing wavelength. Electromagnetic waves are categorized into radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Each type has specific frequency and wavelength ranges. For example, radio waves are used for communication, microwaves for cooking and radar, infrared for night vision, visible light for sight, ultraviolet for sterilization, X-rays for medical imaging, and gamma rays for cancer treatment. Electromagnetic waves are integral to modern life. Radio waves enable TV and mobile communication. Microwaves are used in ovens and radar systems. Infrared is crucial for night vision and astronomy. X-rays are used in medical diagnostics and security. Gamma rays help treat cancer. Ultraviolet rays are used in water purification, and visible light is essential for vision and illumination. Wireless communication relies on specific frequency bands within the electromagnetic spectrum. Medium wave AM, shortwave AM, FM broadcast, TV waves, and cellular mobile radio each occupy distinct frequency ranges. These bands are carefully regulated to ensure efficient and interference-free communication, supporting everything from radio broadcasts to mobile phones. Energy density of electromagnetic waves is the sum of the energy stored in the electric and magnetic fields. It is given by the formula: total energy density equals 1/2 epsilon 0 E2 plus 1/2 mu 0 B2. This energy is distributed equally between the electric and magnetic components. Understanding energy density is crucial for analyzing the power and intensity of electromagnetic waves. Average energy density of an electromagnetic wave is calculated over one cycle. For the electric field, it is 1/4 epsilon 0 E02, and for the magnetic field, it is 1/4 mu 0 B02. The total average energy density combines both, providing a measure of how much energy is carried by the wave per unit volume. This concept is important for understanding the efficiency and impact of electromagnetic waves. Pointing vector represents the rate at which energy flows through a unit area perpendicular to the direction of wave propagation. It is given by S equals E times B slash mu 0. The intensity of an electromagnetic wave is the average value of the Pointing vector over one cycle, indicating the average power transferred per unit area. Both concepts are essential for analyzing energy transfer in electromagnetic waves. Electromagnetic waves carry linear momentum, which can exert mechanical pressure on surfaces. The momentum transferred depends on whether the surface absorbs or reflects the wave. For perfect absorption, radiation pressure is IC, and for perfect reflection, it is 2IC. These principles are used in applications like solar sails and radiation force measurements. Let's look at some practical examples. Calculating the wavelength and amplitude of electromagnetic waves, determining the speed in different media, and finding the energy density and intensity are common tasks in physics. These examples help solidify the concepts and show how electromagnetic waves are analyzed in real-world scenarios, from radio receivers to solar energy. Electromagnetic waves are everywhere, shaping our understanding of physics and enabling countless technologies. Maxwell's equations provide the foundation for their behavior, and the electromagnetic spectrum covers a vast range of applications. From communication to medicine, electromagnetic waves are essential to modern life. Understanding their properties, energy, and momentum helps us harness their power for innovation and discovery. Let's begin with the revolutionary insight of James Clerk Maxwell. Before Maxwell, scientists knew that a changing magnetic field could generate an electric field, but Maxwell argued that the reverse was also true: a changing electric field could produce a magnetic field. This idea led to the concept of displacement current, which resolved inconsistencies in Ampere's circuit law, especially when analyzing the charging of a capacitor. Maxwell's addition unified electricity and magnetism, laying the foundation for electromagnetic waves. His equations showed that not only conduction current, but also the time rate of change of electric field generates a magnetic field. This breakthrough paved the way for understanding how electric and magnetic fields interact and propagate as waves through space. Electromagnetic waves are fascinating because they consist of sinusoidally oscillating electric and magnetic fields. These fields are perpendicular to each other and to the direction of wave propagation, making M waves transverse in nature. Unlike mechanical waves, electromagnetic waves don't require a medium. They can travel through a vacuum at the speed of light. The electric and magnetic fields in an M wave are always in phase, and their relationship is governed by Maxwell's equation. Speed of electromagnetic waves in a vacuum is about 3 × 10⁸ meters per second, but it can vary in different media depending on their permittivity and permeability. This unique nature allows M waves to transfer energy and momentum across vast distances, from radio signals to visible light and beyond. Electromagnetic spectrum is the complete range of electromagnetic radiation, spanning frequencies from just above 1 Hz to below 1025 Hz and wavelengths from kilometers to atomic scales. This spectrum includes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, and cosmic rays. Each type of electromagnetic wave has unique production methods and application. For example, radio waves are used in communication, microwaves in cooking and radar, infrared in night vision, visible light in everyday vision, ultraviolet in sterilization, X-rays in medical imaging, and gamma rays in cancer treatment. The spectrum's diversity enables countless technologies and scientific discoveries, making electromagnetic waves integral to modern life. Electromagnetic waves carry energy and momentum, which can exert pressure on surfaces, a phenomenon known as radiation pressure. The energy density in an M wave is equally distributed between its electric and magnetic fields. The Pointing vector represents the power transferred per unit area, and its direction aligns with wave propagation. M waves are used in countless applications: radio communication, microwave ovens, medical imaging, night vision, and more. Their ability to transfer energy without a medium makes them vital for wireless technologies and scientific exploration. From the sun's rays to X-ray machines and radio broadcasts, electromagnetic waves shape our world and drive innovation.